Hello, this is John Mariella with Side Effect Software. In this tutorial, we will take a look at the muscle displace workflow in Houdini 16. This approach uses muscles to deform a creature's skin without having to perform any expensive physical simulations. We'll start by building basic spherical muscle shapes, we'll rig them up to our creature animation, and then we'll learn how to use them as a layered deformation tool that rides on top of your existing animation. So let's get started. For this lesson, we'll be using this simple model to help us work through the basics of creating a muscle system. When we develop our muscle system, it's not critical that we have a fully rigged creature with animation as I have here, but it is helpful as we can get immediate feedback as we build. The muscle system in Houdini accommodates a nonlinear workflow, so it's flexible enough to add and extend your creature rig without worrying about following a rigid procedure. Let's begin by coming up here to the muscles tool shelf. We'll create a stroked muscle, and the tool prompts us to select a skin object, so we'll select our skin and press enter. This puts us in a stroke state, where our skin has been brought in as our projection geometry. Our cursor also is now armed with the stroke tool, which can have its radius modified by using the mouse wheel. Or optionally, I can hold shift and drag with the left mouse button. If we apply a stroke to the surface of the skin, a proxy muscle is laid down. I can continue to restroke the same muscle until I'm happy with it, and I can experiment stroking the muscle from different angles to get my initial placement just right. While your strokes are being drawn on the surface of your model, the actual muscle position is projected at a depth which you can control here with the muscle depth parameter. I'm clicking this parameter and using my mouse wheel to change the value. By default, we're using the surface normal of the stroked surface to determine how to project that stroke inwards. Optionally, we can change this so that we use the current view direction instead. If we stroke while viewing the surface obliquely, and then modify the depth, you see how the muscle projects in the direction of my view that was current when my stroke was drawn. Let's use the surface normal direction for our example, as this will give us a pretty good alignment. While we're in the stroke state, the radius is still active, so I can continue to use my mouse wheel to modify the radius prior to committing. And this ramp parameter allows me to reshape the profile of the silhouette of my muscle. We later have the opportunity to adjust and refine any of these parameters, so we don't have to get it 100% exact in this state. Once we're satisfied with the initial placement, we can commit our settings by simply pressing Enter on the keyboard. When you're in the muscle stroke tool and you finish creating your stroke and you're ready to return back to object level, you have a few options. You can come up here to your muscle parameters and you can accept your stroke. Optionally, you can press Accept and create a new stroke, which will commit your stroke to the current muscle and allow you to remain in the muscle stroke tool so you can create another. Once you're done with a new muscle, again, you have the option of accepting and creating a new one, or if you press Q on the keyboard, that will repeat the last operation. So by pressing Q, you can continue working in the stroke tool while creating new muscles. We've exited the stroke state and we're back up at object level. And here's our newly created muscle node. If I play my animation, you'll see that the muscle has just been left behind in world space. It isn't moving from the location where it was initially created. This is because it isn't wired up to anything at the moment. Muscle nodes have two input ports. The first is the input for the parent of the head anchor. The second is the input for the parent of the tail anchor. You can tell the head from the tail anchors by their coloring. The head is red and the tail is green. Wiring them up in the network view is no different than wiring any other node. However, we have provided another shelf tool that can make this job a little easier and more visual as well. The Attach to Bones tool takes your selected muscles and allows you to pick your anchor parents in the viewport. This is especially handy in situations where you have multiple muscles and complex rigs, and locating the correct node in the network tree may require a bit of hunting around. When attaching muscles to your rigs, just be aware of the state of the Keep Positions toggle found here on the Handles tab. When it's on, changing the parent of a muscle anchor will not change its current position as the new parent transforms take over. When it's off, changing a parent will put the anchor into the space of the new parent without resetting any of the offsets from the original parent. This is another convenient feature of the Attach tool because if the toggle was disabled inadvertently, the Attach tool will ensure that Keep Position is on when the parenting change happens. It's also worth noting that even though the tool label says it attaches to bones, you're not limited to attaching muscle anchors to bones exclusively. Any object or constraint can be parented to a muscle handle, so this may be helpful when you create your rigs. Now that we have a few muscles stroked, we can start on a bit of shaping work by adjusting our muscle handles. In the viewport, activate the Move state by pressing T. Selecting a handle will allow you to translate it. Press R to get the Rotate handle, and Control R will activate the Pose state, where you can modify both translation and orientation. When using either Translate or Rotate states, you can affect multiple objects at once by holding Shift when you select them. The same is true for the Pose state, but just make sure you switch this setting to the Global Transform handle first, so that one handle will affect all selected objects. For a clearer view of the inner handles, you may want to hide the outer muscle geometry when you make your edits. The display toggles for the muscle components are available here for the currently selected muscle. You can also make use of the muscle's radial menu by first making it the active menu. Then, as you work in the viewport, pressing C on the keyboard will pop it open. This is a handy way of isolating or showing and hiding muscle objects. We can also display the individual components of the active muscle, and we can act on all the muscle objects in our selection at once. This makes quick and easy work of managing your muscles when you want to see the surface of your character's skin while editing the elements nested inside. As I make my edits, I'm purposely pushing these muscles through the surface of the skin because ultimately, I plan on using the outer surfaces of these muscles to bulge the skin out from underneath. On the Geometry tab, we have controls that define how the initial muscle geometry is constructed prior to being deformed by the internal muscle rigging. As we saw in the Stroke tool, this ramp parameter can modify the profile curve for the muscle, and the minimum and maximum values will set the range of how that profile is applied. The handle orientations provide directional control so you can modify the radius or scale of the independent axes along the length of your muscle. The initial orientation of each handle is established by the surface normal vector of the stroke that we drew earlier. The local y-axis of the handles is aligned with that direction. When we're done laying out our muscles, we need to consider this as their setup condition. And this condition would include anything that relates to the way the muscle is initially constructed, like the radius scales and the handle positions. We need to store these parameters in this condition as the capture pose. And we do that by simply coming over to the Capture Deform tab and pressing Set Capture Pose. I'll get into the details of exactly why you need to do this a little later on, but this will essentially freeze a copy of your muscle parameters so that they can be accessed by the rest of the toolset wherever a muscle's capture pose is required. I've gone ahead and attached these muscles to the character rig, and other than just moving along with the bones, they're not doing anything special. To give them a little more liveliness, we can add some secondary animation to them automatically by using the jiggle settings. When we activate jiggle, these parameters get enabled that control the behavior of the jiggle qualities. And even at their default settings, if we go play our animation, instantly you should see some automatic overshoot and spring back in the body of the muscles. We can tweak the type of response we're getting by adjusting the jiggle amount or adjusting the stiffness. And I'm applying these changes to all these selected muscles at once, but certainly you could affect each muscle with its own unique settings. Under the hood, this feature simply relies on a chop network that applies a spring to the position data coming from the animation of the muscle anchors. So consequently, it's a pretty lightweight utility in that it isn't performing any expensive simulation at all. Now, it won't give you anything that's physically accurate, but it does have its uses for some quick and dirty exaggerated movement. Let's move on to seeing how our muscle can be used as a displacement deformer. We'll come up here to the Muscle Displace tool, select our skin object, and then we're prompted to select the muscles to displace with, and we'll accept our selection. And right away, we can see that the muscles are producing this bulge effect on the thigh area. Now, this deformation is happening live, so to speak, so if we scrub to any frame in our animation, we'll see the skin adaptively deform to wherever the muscles are pushing. Let's quickly launch a flipbook so we can get a better look at the effect. Notice how the muscle movement is independent of the skin surface and how the skin slides over and around the muscle volumes. The skin geometry is not bound to the muscles directly. The only binding at work here is coming from the IK bones. If we come over to our SOP network, we can look at how this is being set up. These SOPs here are the original nodes that were in place before we applied the deformer. We have the bound skin here sitting in its capture pose, and here's the deform SOP that applies the IK bone animation. These nodes here were added by the shelf tool. This object merge SOP collects the muscles we selected, specifically the animated geometry of the muscles. It's the surfaces of these muscles that will be used to project the skin towards. This SOP runs a snippet of Python code to reach into the incoming muscles and extract the center wire that it finds there. The points that make up these centers need to be on the inside of the skin, and it's assumed that in your muscles capture pose, this is the case. For this reason, they're collected as static pieces of geometry from the capture pose and then deformed along with the skin by this SOP. This technique of transferring the skin animation onto your center wires will do the job in the majority of cases, but your mileage may vary. In your own setups, you might choose to customize how these centers are animated. And it's here in the muscle deform SOP that these geometries are brought together to produce the bulging effect. The deformer takes your animated skin and projects the surface out away from the centers until it intersects with the muscle geometry. We'll take a closer look at the parameters and controls for tweaking this deformation in another tutorial, but for our basic workflow understanding, I'm simply going to adjust the settings for skin tightness and maybe some smoothing for now. Since this system is entirely procedural, we can do things like add additional muscles to our displacement setup pretty easily. Once an additional muscle has been built and attached to our rig, it isn't automatically incorporated into the displacement. We need to include it along with the other muscles as the displacing geometry. Now, we could come into our object merge node and append the extra muscle to the list, but it's easier for us to make use of the same shelf tool to take care of this for us. Let's come back up and press muscle displace again. We'll select the skin, and notice how this time we're being asked to add or remove muscles. If we press Shift and click, we can add muscles to our selection. If we press Control and click, we can deselect muscles. With all the muscles selected, we'll press Enter. The shelf tool now inserts the additional muscle into the object merge for us, and our new muscle has been included into the mix. When using the muscle displace tool, you may get into situations where areas of skin are affected by overlapping muscles and the displacement isn't correct. Let's look at how we might prevent this from happening with the use of muscle masks. To do this, we simply press Paint Muscle Mask. It asks us to select our skin and accept. Muscle masks are used to limit the displacement amount of a muscle or a group of muscles to specific regions of the skin that we paint with a weight value. When the tool is active, we make use of the Capture Layer Paint SOP, which gives us this pull-down menu to choose one of our muscles as our current region. The idea here is to select a muscle identifier and paint the areas of skin that the muscle will be allowed to affect. Just before we begin brushing, you'll notice that all of our muscle displacement has been disabled. It's not until I begin laying strokes down that the bulging we had before becomes apparent. And this is due to having all of our weight masks initialized to 0 just prior to entering this paint node. In this way, the Capture Layer Paint SOP will contain all the absolute weight data locally and not be relative to any changing values that might be coming from upstream. Now, while it might be useful to see the displacement happen as we paint, it may not be the quickest way of working. Let me turn off the material display to make things a little clearer. And if we look at the chain of operators in our SOP network, here's the paint node that I'm interacting with. That's feeding into a deform SOP, followed by our muscle deform SOP, And for every stroke I make, these deformations need to be calculated as the viewport is updated. Since I'm pretty familiar with my simple muscle layout, I know roughly where my muscles should be having some effect. So I can cut some of this work short by moving my display flag up to the same node I'm painting with. And now I won't see my displacement anymore as I paint, but I won't have to pay for it either. To paint with another muscle ID, I can come back here to the pull-down menu and select a different region. But it might start to get confusing if my muscle naming wasn't entirely logical. So it might be helpful to use a more visual approach to pick my regions. If we display the other objects in our scene, we can use Control middle mouse button to select our muscles. And you'll notice that the pull-down menu updates as I make my selections. So now, with the visible region loaded on my brush, I can paint confidently knowing that I'm in the right area, but maybe blindly as the muscles are blocking my view. So I can use spacebar Y as the scene visibility toggle to quickly clear my view while I paint, and spacebar Y to bring them back to make more selections. And with our mask painting coming along, let's move our display flag downstream of the muscle deform SOP to see how our deformation is looking. Sometimes you'll find that it might make more sense to have the muscle deform SOP treat a collection of muscles as a group rather than individually. Think of this as giving clustered muscles logical names for paint masking. Every muscle object is equipped with a muscle ID parameter, which is meant to serve this purpose. By default, the muscle ID parameter is set to the expression variable $OS, which simply expands to the object node name. This just means that every muscle is given a unique ID just like its name. By overriding this default, we can take a collection of muscles and give them a common shared identifier. For example, let's change the ID string for these three muscles to L-phi, so that they all have the same ID. And for this muscle, let's leave the variable expression in place, and instead, let's change the node name just to demonstrate how $OS behaves. All muscles being fed into the muscle deform setup get stamped with a point and primitive attribute named muscle ID. The value for this attribute is the string which we just modified, that is L-phi and L-calf. And to reiterate, the attribute exists on both primitives and points. This just simplifies access to these values further down in the deformer. The muscle deform SOP will then use this attribute to match up muscles, centers, and weight masks to ensure that the bulging happens in a very controlled way. The muscle capture SOP is responsible for making the initial link between your muscle IDs and your weight masks. This parameter specifies the attribute to use to distinguish region names and assign weights to. There is also this radius parameter, which is used to weight skin points based on distance to each muscle. But for our purposes, we aren't going to use the proximity weighting, so this parameter can be disregarded. In this next string of SOPs, this is where we effectively zero out the weights. We're only interested in keeping the initialized region arrays, so we can rely exclusively on our painted values. If we take another look at our region pull-down menu, we now have the newly named muscle ID regions included in the list, L_thigh and L_calf. The original region names, stroked muscle 1 through 4, also remain in the list, even though they're obsolete now. Remember that the muscle deform SOP will only act on muscle IDs that match. The IDs named stroked muscle no longer exist. So you may ask, why are the original names still listed? These IDs are still hanging around because the paint node already had values painted for these regions before the muscle ID parameters were altered. The paint SOP isn't going to delete this paintwork unless you tell it to. And this is okay for our demo purposes, so let's clear out these masks before we start painting the properly named regions. We reset all changes on the Capture Layer paint SOP, and now we see that the only regions available to us are the muscle IDs coming in from the SOPs upstream. Also, as we use Control middle mouse button to select our regions, we will now see that selecting any of the quadricep muscles will activate that shared ID that we defined with our L-phi override. Now we can go ahead and paint our weight masks for these clustered regions to get our deformation working properly again. With the masks now painted for the L-phi and L-calf groups of muscles, let's move our display flag back downstream of the muscle deform SOP and see that our deformation is behaving much better. The overlap anomaly we were getting earlier is now being avoided. In typical creature setups, you'll be looking at scenarios like this one, where you conduct most of your work on one side of your rig and then rely on mirroring to copy your work across to the symmetry plane. It's usual best practice to make sure your node naming follows a standard naming convention. If you use a simple prefixing convention like we're using here to represent left and right sides, you'll find that you can rely on a bit of proceduralism to save you a bit of work. With our muscles in place, we can add our mirroring step. Let's press the Mirror tool button, and as we select the muscles we want to mirror, we should note that this is the same generic mirror tool that we have on the Modify shelf. So that means it's not going to act exclusively on muscles. Anything you have selected will be mirrored. So let's be sure to only mirror the muscles that we're interested in by selecting them here in the network view. And we verify that the ghosted copies are mirroring in the correct plane. Also, as we are in the mirror state, we can use this input field here to perform a search and replace operation on the newly created copies. With the parameters set this way, we'll rename all copied items so that any prefix up to the first underscore is stripped and replaced with an R underscore. Let's press Enter to accept the mirror operation. And there we have our symmetrical copies. Here in the network editor, we see that the new nodes have all had their prefix replaced. And the mirror function also took care of examining the inputs to these nodes. And if they were connected to a parent that appeared to follow the left-right naming convention, then the new nodes were automatically attached to parents on the mirrored side. Looking at our animation, we now see that the new muscles are all attached to the correct bones, and they are also animated with the same jiggle settings that the original muscles had. However, you may notice that while the muscles are duplicated, their influence on the skin has not been copied. Like the addition of the calf muscle earlier, we must include any new muscles in the muscle displace setup. So let's repeat those steps. We'll press Muscle Displace, we'll select our skin, and Accept. And as we're prompted to add or remove muscles from the displace setup, we can visually confirm the muscles that are already included by their highlighting. We'll shift-click to select the new muscles we want to include, and Enter to accept. Let's examine what we have now. Our muscles are all being included, the centers are also being fetched properly, and they're moving along with the animation. However, looking at the deformation we're getting, we see muscle displacement here on the left, but no displacement on the right. The reason for this is simple. The weight masks we painted earlier restricted the deformation to happen only where we have non-zero values for L thigh and L calf regions. And because the muscles on the right side have their own muscle IDs, they are not being allowed to have any effect on the skin. In the region pull-down menu, we can see that the mirror utility also took care of applying the same prefix logic to the muscle ID parameters on the copied muscle. And since we don't have any weight masks painted for the R underscored regions, they aren't contributing at all to the deformation. So we have a couple of options at this point. We could select the new regions and paint the masks manually, or we could get some help from another mirror tool. Just before activating the tool, let's leave the display flag on the deformed output so that the tool can properly detect and recognize the nodes involved. Let's press the Mirror Muscle Mask tool, and since our skin is already selected, we're prompted directly to select the points that will receive the mirrored mask weights, the destination points in other words. To help us make a more accurate selection, let's view our model in a front ortho view by typing spacebar 3. And we'll go ahead and drag out a selection of the destination points, and we'll press Enter to accept. Next, we're prompted to select the muscles that we want to have mirrored. Spacebar 1 will get us back to the perspective view. And as we verify that the selected muscles are correct, we might find that we have to shift-click to include any muscles that may not have been detected automatically. Pressing Enter, and next we're asked to select the destination muscles. And it looks like it detected the right ones for us this time. So we can enter to accept that selection, and the mask mirroring is now complete. We can see by the mask pattern that the right side is now a mirror image of the left side, ignoring the coloring being used. You'll find that the use of painted masks will not only give you some control over errant deformations, but they will also provide a bit of efficiency in the displacement calculations. The deformer will only spend its time projecting skin points if it finds non-zero values for any of the muscle IDs it encounters. So it's usually a good idea to include some amount of masking. Just before we wrap up this lesson, let's take a look at another slightly more complex example that makes use of the same workflow. Here we have an animated horse that is set up with our basic bone capture and deform rigging, and much like our earlier example, the skin is bound to the bones and is quite smooth, and lacking in detail and secondary animation. I have already gone ahead and created muscles for this rig, and as we display them, we'll see that I've created a pretty dense arrangement. What I wanted to demonstrate in this case is how we might use basic muscle shapes to produce some compound effect on the skin by simply layering and overlapping muscle objects. One nice feature of this workflow is that you don't have to worry at all about muscles intersecting and moving through each other, since we're only trying to mimic the surface qualities of a mass of muscular forms under the skin. This also means that you could use muscle objects to represent internal shapes that may not be anatomical muscles at all. Like the abdomen in this case, I can use a single shaped muscle object to move along and have secondary jiggle and get the effect of internal body mass bouncing along inside the skin. In more complex setups like this, if the number of muscles begins to weigh down performance, you may find it helpful to temporarily deactivate all jiggle and activate it only on the muscles that you want to fine-tune. Even though the chop networks that drive the jiggle animation are relatively lightweight, you should expect some lag as the number of muscles increases. For interactive playback while you adjust the jiggle settings, you may also rely on viewport isolation to only display the muscles you're focusing on. Let's display our skin once again and take a look at our deformed result. Notice how there's much more detail and sculptural quality coming through from the muscle displacement. And with the jiggle reactivated on all our muscles, we can launch a flipbook to see the results in motion. So that will conclude this tutorial. I hope I've been able to demonstrate how these simple tools can be used to create some interesting effects in a creature rig, and I look forward to seeing how these tools might find their way into your creature animation soon. Thanks for watching.